think I got everything. Excuse me. So I'll begin with a word of prayer. By the way, here's your handy dandy top hat coat up here if you thirst after top hatting. So, dear Heavenly Father, we thank you for this day. Again, I thank you for this class. And for the students, just ask you to just bless our work today. Help us to understand a little bit more about logarithms and how they work and how to solve equations with them and everything, Lord. And we just thank you again, Lord, for your many blessings to us. In your name I pray, Lord Jesus. Amen. So what we have here is just a quick recap of, these are the laws of exponents, right? These are the laws of exponents. So if we have the same base and we multiply, we add the exponents, right? If we exponentiate an exponential function, we multiply the exponents, right? When we have two different bases, both to the same power, we can combine like that. And if we have a quotient, we subtract the denominator power. A to the 0 is 1, a to the 1 is a. So we defined the logarithm last class as the inverse function to the exponential. So these identities are key, right? But what is probably new are these guys right here, right? So these are newfangled identities that we'd like to get used to those. So I'm going to do some examples to try to, help you to learn these identities, all right? And I probably won't prove these today. I'm going to put off the proof of them until a future class, all right? You're like, well, you don't have to prove them. It'd be good for us to prove those. I'll tell you what the proof is basically. The proof basically is just that if you translate the laws of exponents into the logarithmic notation, it implies these. That's actually what ends up being the proof. But it'd probably be better for us to just use the properties today. So let's do that. First of all, a cautionary tale. Example 1. If I have log base 3 of, let's say, 27 times, 3 squared, right? What can I not do? What I cannot do is to say that in fact, it's not equal to 2 times the log base 3 of 27 times 3. All right? What's the problem there? Why can't I pull the 2 down? What's the situation? Notice that the property over here, right? It's that the whole thing is raised to the p power, not just part of it. See here, I only have 3 raised to the square, right? So I can't, it's not proper, it's not true, in fact, that you can simplify like that. How do we work this out? Well, this is equal to log base 3. 27 is 3 to the 3, right? 3 squared, which is log base 3 of 3 to the 5 power. And then that is equal to 5. So that's true. It is equal to 5. What would happen if we kept going on the thing that's on the top of the board? How would that work out? This would be 2 times log base 3 of 3 to the 3 times 3 to the 1. So we'd have 2 times the log base 3 of 3 to the 4, which would be 2 times 4, also known as 8, also known as not equal to 5, right? So as you can see, trying to just half apply these properties, it doesn't work. Like, it has to be exactly that pattern in order to do it. Not kind of like the pattern. It's got to be the pattern. All right? Otherwise, you get errors. Any questions? All right, so let's go on. Let's just try out these things here a little bit. So example 2, let us expand the log. Expand the log. All right, so here we go. We've got log of, let's say, 1,000 x divided by the square root of yz. All right, I think at this point it's time for me to confess to you that there are two popular logarithms that we need to know about, two common ones. That's kind of an unfortunate pun. In fact, this is the common log, quote unquote common log. And so for us, log is log base 10. What's the other one that we like to use? The other one we like to use a fair amount is the natural log. Natural log. And that one we use ln for, which actually means log base e, where the e is Euler's number. It's about 2.7-ish. All right. Okay, so example 2, we're up against the common log, which means it's log base 10. All right, so I'm going to go ahead and I'm going to use my properties of the log to expand this. And here it goes. Here it goes. So we've got ourselves a log of 1,000 plus the log of x minus the log of the square root of yz. Is everybody with me so far? What did I do? I did a product. So where there's a product, there's a sum. And where there's division, we have a minus. Make sense? So what I did was I used, this property, the top two properties in the purple box, like that. The last class, I expanded this out into 3 steps and they complained. So I'm trying something different with you guys. All right? So there we go. You could make this into 2 steps if you wanted. Now, this is really the log of 10 to the 3rd power plus the log of x minus the log of yz to the what? The 1/2 power, right? Square root is the 1/2 power. Aha! So we can use, now there, check it out. That 1/2 is, the whole thing is to the 1/2 power, right? The whole input to the logarithm is to the 1/2 power there. So it's proper, it's fitting, in fact, to pull the half out by the power property to log, this property right here. I can do it. So we do that. Oh, by the way, what's the first thing? What's the log of 10 to the 3? So right here, log base 10 of 10 to the 3 equals to 3. That's the pattern. That's just 3. All right? 3. Log of 1,000 is 3. Log of x is what it is, so keep that one. And then we've got minus 1/2 the log of yz. All right? Now, we're not done. We're trying to expand it as much as is possible. Okay, that's our current task, is expanding it. So what can I do? What can I do with the log yz? This right here, what can I do? Log of the product is the sum of the logs. That's the property here. So what we got is 3 plus the log of x minus 1/2. I'll put some parentheses in here. And that's log of y plus the log of z. And so what do we have? We have 3 plus, excuse me, goodness gracious, minus 1/2 log of y minus 1/2 log of z. Now there's a problem in your homework that's kind of like this, problem 87. But problem 87 also has a little bit extra. It says for you to write your answers in terms of A, B, and C. All right? It says write your answers in terms of A, B, and C. And in that problem, it tells you to think of A as being the log of x, b, now it may not be exactly this, but it's something like this, okay? Basically this idea. It may be natural log in the homework problem, I'm not sure, I don't remember for sure, but it's like this. All right, so if I say write your answer in terms of a, b, c, where a is log x, b is log y, c is log z, what's the answer then? It's 3 plus a minus 1/2 b minus 1/2 c. It's just a silly substitution, but there it is. Any questions? Physics, what's that about? Let us go the other way. Let's collect the logarithms into a single log. Example 3. Collect into single logarithm. And so here, we're going to start with, let's see here, 1/3 the log of 1/3 the log of x minus 3 log of y plus 4 log of z. Let's see here, plus 2. Plus 2. We'd like to write that as a single logarithm. How is that accomplished? So I'm gonna work on it down here, if you guys don't mind. So first of all, I can pull the third in. That gives me log of x to the 1/3, right? And then let's see here, minus the log of y cubed plus the log of z to the 4th. Okay, so what I did here was I just brought the numbers out front into powers of the log using the power property for the log, right? What about that 2 though? How can we, the 2 is annoying, isn't it? What's that? Common log? Can I just erase it? Just erase it. Just erase it. If you don't see it, it's not there. I think you might. Well, I think you have a future in politics. That's good. Politics is like a science of simultaneously ignoring real problems and inventing ones that aren't actually there. It's like both of those things all at once, right? So, so 2 is actually, check it out, log base 10 of 10 to the 2. Aha! We can use this trick. If you want to make a number into a logarithm, simply use the definition of the log to convert it into a log. I'm just using this identity right here to convert x into a log. All right? So that means that 2 is actually equal to what? The log of 10 to the 2, log of 10 to the 2, which in this case is 100, yeah? So 2 is the log of 100. You just got to use your imagination a bit. There it is. And now, let us combine. So what we got is the log, big parenthesis here, x to the 1/3 times z to the 4th times 100, all divided by y cubed. There you go. We collapsed the logs into a single logarithm. I hope you guys don't mind. I'm using the like these two properties down here, the last two properties, together at once. You see how it works? Anything that's got a plus on it appears in the numerator multiplied. Anything that's got a minus appears in the denominator as a division. That's the pattern here. All right? Are we good? So there it is. So there's problems like this in your homework. There's lots of problems in text like this. The purpose of these problems is for you to internalize and learn the logarithm laws so that you get good at them. All right? I personally don't think these kind of problems in and of themselves are really that interesting. To me, it's more interesting how to solve equations, right? I think solving equations is kind of the more interesting thing we do in here. So let's get back to that. Let's solve some equations today. And of course, I still owe you guys a discussion about like what's the graph of the logarithm look like and all that jazz, but we'll get back to that some other day. I don't want to talk about graphs of logarithms today. So all right, so I'm going to start us my example 4 here with a problem that we could have solved last class, but I'm going to solve it in a new way to emphasize the technology that we now have in hand here. So example 4, suppose you want to solve, let's say, 10 to the, I don't know, 3x minus 2 is equal to 10 to the x squared. Now, of course, how could we solve this last time? What would we have done? What did we do? We just said one-to-one property, right? One-to-one property, so we can equate the exponents. And that's true. We could do that. Nothing wrong with that. But we've got another way to look at it. See, now what we could do is we could take the log of both sides of the equation. We can take the log of both sides. And we can take, so we've got like log of 10 to the 3x minus 2 is log of 10 to the x squared, do you see? And as such, as such, we get 3x minus 2 is equal to x squared. Now, of course, that is exactly where you would have gotten to start with by using the 1-1 property. But I'd like to point out to you, we can think of it as taking the log of the equation. Okay? And then we can solve it. We've got x squared minus 3x plus 2 equals to 0, which is x minus 1 times x minus 2 equals to 0, which gives us solutions x equals to 1 or x equals to 2. So that's not bad, right? But let's try something a little different. What if instead of this problem we face the following one? What if we're up against 10 to the 3x plus 8 is equal to, I don't know, 3 to the 2x minus 1? Now what should we do? See, if I take the log base 10 to both sides, that makes the left-hand side nice, but it makes the right-hand side ugly. If I take the log base 3 of both sides, it makes the right-hand side nice, but it makes the left-hand side ugly. All right? So to make both sides ugly, I'm going to do something different. I'm going to take the natural log of both sides. And the reason I might do that, the reason I'm going to do that, is because if you look at your calculator, you've got a nice big old natural log button on there you can use. Now you also have a common log button probably. So those are the two buttons that are almost on all scientific calculators, is like log base 10 and the natural log. If you fiddle around with a given calculator, you may have logs of other bases, you may not. It kind of depends on the calculator. So we got to talk more about that. There is a workaround. with the math if you don't have log of another base. But I'm going to take the natural log of both sides. Again, just to illustrate the method here. So 10 to the 3x plus 8 is equal to the natural log of 3 to the 2x minus 1. This is something you can do to an equation. You can take the natural log of it. Now, what can we do now? Well, we can use the properties of logs. See, because I can pull that out, and I've got a power here, which I can pull out, and that gives me 3x plus 8 times the natural log of 10 is equal to 2x minus 1 times the natural log of 3. Which, now don't be afraid. Natural log of 10 and the natural log of 3. These are just numbers. You can put them in your calculator. You can find a decimal, but we'll just leave them. They're numbers. We're happy to have a natural log of a number in our answer. That's usually fine. Now sometimes I'll ask you, please leave your answer in decimal form, and there I actually want you to plug in the natural logs and like simplify it into a decimal expansion. If I want that, I'll ask for it though, okay? So how do I solve this? Nobody? How about this? I put all of my x's on one side, right? And everything without an x on the other, right? I'm pretty sure there's a Taylor Swift joke in there somewhere. If I reword that slightly. Obligatory. Minus 2x log 3 equal to minus 8 times the log of 10 minus the log of 3. Do you see what I did? I just put all the x's on one side and everything without x on the other. I'm trying to solve for x, so what do? I factor x out. Factor x out. This gives me x times 3 log 10 minus 2 log 3 is equal to minus 8 log 10 minus the log of 3. Finishing move, divide by the coefficient of x, and there we'll have our solution. So here it is. X is equal to minus 8 times the natural log of 10 minus the natural log of 3 divided by 3 log 10 minus 2 log 3. Now, and there you have it. I mean, it's ugly, but there it is. So if we're up against an exponential equation where you have different bases on the different sides, taking the natural log allows you to solve it because of the algebra I have on the board right here, right? It basically undoes both of the bases at once at the cost of introducing these ugly natural log of 10 and natural log of 3 things. But it's going to be ugly however you do it, because this problem is a mixture of two worlds, the base 10 world and the base 3 world. And, well, you kind of don't want to do both at the same time, right? Do you guys know what 1, 2, 3 is base 10? I mean base 3? What's 1, 2, 3 base? Oh, that wouldn't even make sense. What's 1, 2, 0 base 3? That means 1 times 3 to the second power plus 2 times 3 to the first power plus 0 times 3 to the 0 power. So that's actually equal to like 9 plus 6 plus 0. So 1, 2, 0 base 15 is actually 15 base 10. Right? You don't want to work in both. You don't want to be in both worlds, right? You guys, if you were taking Math 114, you could be doing this right now. I think that's in Math 114. I don't know. One of the other Gen Ed math classes does this stuff, but we don't do it in here. Wait a minute, we don't do it in here. My apologies. There, I fixed it. I need to leave time for calculus. See, now that we've done all the log properties, so next I just need to do like trigonometry.
No, thank you.
Man, you guys are like,
I think we should just look at the quiz solution and then
okay, fine. We'll just look at the quiz solution and call it a day. She's not wrong. So annoying. Could I do like one class of calculus? Just like all of calculus in one class. How about that? I could have like a summary calculus class.
You literally have a class that teaches calculus.
No, I can't. Well, what if I add to that? You don't have to come if you don't want to. Oh, then all of a sudden I'll have participation in this event, right? I just have to add that you don't have to come if you don't want to, right? All right, where'd that thing gone to? I had it open, but then my computer decided that it had no internet, which meant I realized that my computer needed to what? No. Well, you got quiz 8. I'm looking for quiz 10 solution.
It's right.
Well, it is quiz 8 for you guys, but it was quiz 10 when I solved it. So here it is. So number 1, is it a one-to-one function? There's 2 ways to go: graphical or algebraic, right? If we do algebraic, and I will post the solution in Canvas, so you know.
Oh, it's not on Canvas right now.
Not yet, no.
Okay.
I usually post it, but my computer broke on me at the start of class today, so I didn't get to do it yet. But I will get to it. Hopefully soon. Maybe before I leave today. We'll see. All right, so where'd I put my laser? My laser. Oh yeah, either way, I didn't say. So either would be legit. You can either say f of a equals f of b and find a's plus or minus b, so no, not one-to-one. Or you could make a graph and show it fails the horizontal line test, not one-to-one. Those are your 2 flavor options here, since I didn't pin you down one way or the other. Now, problem 2, I hope you guys got. Problem 2 here is to find the inverse function. So what we do? We write y equals the formula, and we solve for x. And so how do I solve for x? I put all my x's on one side, and no x stuff on the other side. So after multiplying out, I got all my x's here, and nothing without an x over there. Factor the x out, divide by the coefficient of x. Hey, this is the same algebra that we were just doing in the last example in class, isn't it?
Yes.
In fact, this same algebra comes up over and over. And learn this algebra, and then, you know, that's good for you. Yes, you do not have to change the sign. I changed the sign because I try to stay positive. So, and although it seems like there's an error. Ooh. No. Oh man, look at that. If I multiply this by, if I try to factor out a minus from the top, like factor out -1 from the top, if I factor out -1 from the bottom, I should have a minus y here. That's a mistake. My apologies. Yeah, this is an error. Yeah. Did you guys not have that and you had a minus?
How come we can't just keep it x equals -2y minus y?
That would also be fine. That would also be fine. I try to get rid of minuses, generally speaking, just as a point of mathematical etiquette. But what's less important than getting rid of minuses is keeping a correct answer. And this is incorrect, right? I factored the minus out wrong. I got too carried away. I tried to make it too positive. And that affected my answer as well. No, rats. See, that matters a lot here. As you can see clearly from this cannot be 3, right? But after I made this error, I got tricked into thinking y could not be -3. Nobody in the last section told me this at all. They probably just wanted to leave. So, but anyway, hey. So yeah, we should mod out, we should avoid positive 3 because we should be working with that formula basically. So 3 is not allowed for the domain of the inverse function, but remember the domain of the inverse function is the range of the function. And on the other hand, the domain of the function is just where we can't have division in the denominator, namely at -2, because there's an x plus 2 in the formula for the function, right? If I go back up. See, this x plus 2 here is what makes me throw -2 out of the domain of the function. That would also be equal to the range of the inverse function, right? All right, so sorry about the error there. I guess I better go fix it. Next, here we have this one. You probably could have done in the style of last class if you wanted to. Just convert to base 2. You got 2 to the x squared equals 2 to the 6x. 1-to-1 property tells you x squared equal to 6x. Factor out your x. And you got x equal to 0 or x equal to 6. Hooray! All right. This one, we have to use the technique that I just showed you in the last example for class, right? Take the natural log of both sides, use the power property, put all your x's on one side, factor out the x, divide. There you go. That's how you do it. And then finally, last but not least, we've got the inverse problem down here. This is easy if you know what you're doing. If you don't know what you're doing, I just don't even know what you think when you're looking at this problem. I mean,
How can you figure out if it has no inverse?
if it passes the horizontal line test, it has an inverse. If it doesn't, it doesn't.
Okay.
Yeah. So, passes the horizontal line test. And what you do is you just take the points that are on the graph, right? Which you can see because I got graph paper here, right? And you just take them and you flip them. So -8, 6, I trade over here for -6, 8. My -4, 4 goes to 4 minus 4. My 6, 8 goes to 8, 6. As a final check on my answer here, notice that the domain of the given function is -8 to 6. The range of the inverse function is -8 to 6. The range of the given function is -6 to 8. The domain of the inverse function is -6 to 8. So we've got the necessary flippity-flopping between the domain and the range of the function and its inverse. That's a good sign. And also, the picture is symmetric about the line y equals x. So that's what you want to see there. Anyway, thanks guys.